Those of you who've seen me in the past know that I have a wonderful voice, just like George Clooney. But today I have a cold, and I have a frog in my throat, so I'm going to do my best. But after arguing with Doug Selfall last night at dinner, it's kind of worn out a little bit. A little louder. Louder? Yeah. Yeah. We'll do what we can with that. Okay. This is the... Now, you know how I do speeches. I gather up all the great illustrations I've got, I string them together, and then I put them on the screen, and then I make comments about each one. It's the laziest way that I can think of to generate a speech. So if we can see number one.
I'm learning.
That's right, it's just the title. Ta-da! I wanted to spend just a couple of minutes explaining that for a lot of people, it's been a case of waiting for quite a long time for linear systems to get those LSJ74 P-channel JFETs out. These are the ones that replace the discontinued Toshiba parts along with the Toshiba 2SK170s. The only FETs that are really quiet enough to do a really great job on the input of a moving coil stage or a lot of other things. And they have the LSK170s out, and they're even at a reasonable price, and of course they're highly recommended. But everybody's been waiting for the Ps, and there have been a few manufacturers who have simply purchased all they could back when they were still available and are hoarding them. I'm proud to say I'm one of those guys. But Paul Norton recently sent me some samples of the LSJ74s. Sent me actually two different sets of samples, which, as far as we can tell, the labeling was confused. So we had two sets of parts, and they were being evaluated by us for suitability for replacement, 2SJ74s, and power amps, buffers, line stages, all the usual stuff. And of course, the thing that is fairly critical for everybody, noise. If I can have the next one. First thing I did is I built up a little circuit. You can understand this circuit. There's the JFET. The source is running through 10 ohms to ground. Of course, it's biased negatively. It is a P-channel part. I have an input, capacitively coupled, and a little circuit that I can use to set the bias up to set the point. The point of bias that I tried this on, and I screwed around a little bit, but I found something that worked fairly well. It was 10 milliamps worth of current, and I started out with a drain voltage of 10 volts, and I also tested at 20 volts, and it went into a 2.3 k ohm load, and this is the test circuit. And what we did is I just subbed in 2SJ74s and LSK74 prototypes. Next one, please. This is the set of curves that I got. This is an interesting set of curves. The two lower ones, this one and this one, are the 2SK17, the 2SJ74 and the LSK74. And I'm going to let you guess as to which ones they are. No, okay. This is the 2SK74. And this is just simply distortion versus output for the circuit that I mentioned. When I put in the 2SJ74, I've discovered that 10 volts was very close to what we call the sweet spot. In other words, the output drain resistance of the part characteristic happened to cancel the second harmonic out rather nicely as against the transconductance characteristic. And I got this incredibly lower distortion curve. And if any of you have read the article that I wrote on this called The Sweet Spot, this is a favorite little technique of tube guys trying to get very low distortion. And in fact, it just so happened that we hit it with the 10 volt arbitrary figure. This is the LSJ74. And as you can see, if you want to tweak the voltage and current around that, you can do quite well for yourself, particularly at some of your lower levels. At 20 volts, I got these two curves up at the top. We're outside the sweet zone of both of them. By the way, the 2SJ74, the sweet spot on it was at about 6.5 volts or so, quite low. Actually not usable in a lot of cases for that sort of thing unless you're cascoding. But so there are some subtle differences, but this one is actually rather convenient. There's a there might even be reasons to prefer this part occasionally. Up here, you've got two relatively close figures here, and this is the 2SJ74 in the green, and just above it is the LSJ74. And I would say that this curve demonstrates that for all intents and purposes, this is pretty inconsequential difference in performance. In other words, if you're using this part for front ends in power amplifiers or followers in line level stages or all the ordinary line level applications that you're thinking about, you can just plug it right in. It biases at a slightly different level, but part of that is that I had BL figures for the Toshiba parts, the BL selection, and these appeared to have been a higher IDSS current. In other words, if they had been Toshibas, they probably would have been called V parts. Now, the V parts are in some circles the most prized of all. They're certainly the most expensive ones to get. It appears that that is, in fact, what Linear Systems is just simply delivering. And I only had a reasonably small sampling. And the sampling that we had was broken out into two. Paul Norton was looking at potential applications, or at least trying to get some sense for how critical the noise figures might be for some of these kinds of parts in terms of what they bring to market. And the fact of life is that unless you're using it at the input of a phono stage, particularly a moving coil stage, it's not, it's not that much of a difference. I would say it's essentially negligible in my book. If I can see the next, Wayne ran these up on the HP vibration analyzer that he runs. I just commented the other minute that I didn't know that we had bought him such an expensive piece of equipment. So these are the 20 hertz differences between the two sets of samples of the LSJ74s, one which had been marked high noise, don't use, bad, and the other was, and then ones that were marked good. Unfortunately, they seem to have been mismarked because the bad ones are down here and the good ones are up here. But I'm going to assume that it was just that kind of clerical error. Down here, by the way, also is the Toshiba part. In fact, I don't even happen to know which one it is. And if you look at this, it really doesn't matter. We're in the zone now, too, by the way, that if you throw a 10 or 22 ohm resistor on the source, or a slightly larger value on the gate, the noise values of the resistance themselves are going to start owning this curve. This is a short part of my presentation. The essence of it is twofold. One, it's going to be safe to go in the water. These are really going to be great parts, and I'm here to endorse them so that people can feel comfortable while putting them to use. The other is that I have been told that Linear Systems is either making an announcement or is going to make an announcement very shortly regarding the availability on these parts. I'm assuming that, in fact, the very fact that I can get a hold of good-looking ones I've been told that it's quite soon. So, main thing here is I'm here to spread the good news, and I'm independent. In other words, I'm not. Aside from the fact that Linear Systems runs my projector here for me, I have no other economic interest, and in fact, I still got a couple years worth of Toshibas to run through before I can use these. Okay, next. This is the part where you can ask any questions.
What's VDS on the Linear Systems part? Is that still 25 volts?
I don't know the rating. I ran them up to 20 volts, and I didn't even bother to look. If they are, the ratings on these are a little funny in the sense that everybody is very concerned about gate leakage on JFETs because the input impedances are so incredibly high, and a lot of people who have instrument applications are very interested in that. If, in fact, you actually say, well, what can I take these up to before they start breaking? My experience is about 43 volts. In fact, 43 volts. Now, any other questions? Okay. I mean, Doug's waiting, so we'll move right along. Part 2, the burning amp number 3 front end, which you have seen published on the pages of DIY Audio, or maybe not. This is I just thought I'd tweak this for you guys only, and the rest of the world can hear about it tomorrow. The balanced burning amp, the balanced version of this circuit. Okay, next picture. This is my handsome picture, the one that I stuffed myself. And this is oh, there we go. And this is the stock piece, except that, let's see, where was it? These two resistors get tied together instead of to ground. So you peel them up and let them talk to each other, and you now have the BBA3. Next picture, please. Nice caps that you notice that we use there. This is the standard BBA3, only there's 2 of them, and everything else is the same as ever, except they got plus and a minus input now because it's 2, and they talk to each other out here. And there is a 200 ohms worth of resistance connecting between the 2 10 ohms here and the 2 10 ohms there, and you now have a balanced version of this piece. So if you happen to buy the boards that are nicely for sale on DIY Audio, what you do is you get one board to make, instead of 2 channels of single-ended, 1 channel of balanced. And this gives the same gain figure. Used to be 100 ohm and 100 ohm, and this is what it is now. Next picture. This is the set of distortion curves. Now I set this up. This circuit was designed to be a front end for a power amp with a follower output stage. And in this particular case, with the BBA3, it's the first time that we put one together that had no feedback on it. It uses only degeneration, which is arguably a form of feedback, but as also arguably said, a different form of feedback. So here is in purple and red the distortion versus equivalent output power. In other words, if we were driving a perfect follower with this front end, this is what the power versus distortion figures would look like. And these are the original BA3 numbers here, and they are for 24 volt and 32 volt rails. And so you can see on the red one, for example, it's got more power. So for instance, 24 volt rails, you can get, 25 watts at a 1/10%. And with 32 volt rails, you can get up to about 50 watts, which is real nice. If you go to the balanced version, however, you'll notice that it jumps right up there, and it not only has a lot lower actual numbers, because it just so happens that it does a reasonably good job of suppressing second harmonic. What you see for a distortion waveform is third harmonic, fairly pure stuff. There it is, and at 24 volt rails, you've got a 100 watt amplifier, and at 32 volt rails, which is the maximum for these kinds of parts, you have got a couple hundred watts. The reason that the maximum, on this is that we are using those 2 SK170s, 2 SJ74s from Toshiba, and they really break at 43 volts, and I try not to abuse them much beyond the 30 volts or so. So this is a nice quickie, but here it is, easily built, and you can use it to drive high power output stages. Sounds real good. It's a very nice little circuit. Next picture, please. Oh, here's the distortion versus frequency for that. And this was at, let's see, 5 watts and 100 watts. And normally, you start getting up at high swing, you start seeing the distortion climb. Not so bad. There it is at 100 watts, and it goes from 0.1 up to about 0.2. Down at more reasonable levels, it's just sitting around there. Next picture. 1 decibel down to 200K. Now my AP at home is a half a decibel at 200K, so probably about half of that is the audio precision, and the other half is the circuit. So let's see. Next one. Oh, common order. We just balanced circuits. So and by the way, it has very high input impedance. couple hundred K, well, actually whatever you care to put there. The common mode rejection on this, which was done with the equivalent of a 1 watt input level, is quite high. It's 80 dB down at 1K. And to explain quickly, common mode is the ability of a balanced input stage to reject noise, which is the same on both channels. So what we're doing is we're feeding in 2.8 volts of what we would be calling noise that we don't want, and we're seeing how much of it makes it to the output. Well, 0.01% of it makes it to the output at a kilohertz, and that slowly declines, and it's 60 dB down at 20K. Next picture. Questions?
The output stage that, with the high bias and the high power, that would be a complementary push-pull, or
Not necessarily.
just kind of whatever you want to build and how much?
Sure, whatever kind of, well, the idea is you're probably using some kind of follower, because this is designed to develop the voltage that would be followed by something. Now, of course, there's a lot of possibilities for different kinds of followers. The most obvious sort of would typically be a push-pull Class A is probably the go-to application for this, but I have built some nice single-ended circuits that balance single-ended. There's an oxymoron, balance single-ended, and works great. But also this has got a fairly low output impedance. Let's see, what is it? It's 300 and something ohms on each leg, so it will drive a fair amount of capacitance, and so it's not really typically going to be any real issue. In fact, I think it was somebody, but I used it to test some other circuit. Any other questions? Next slide. The beast with maybe this is the one. The beast with 1,000 JFETs. Now you recall, I spelled it right. You recall that last time I was here, I showed you a stuffed photo of the board, and I was waving it around. And since then, the guy that I have as an intern came back this last summer and finished the job. So if we can see the next. This is the basic element of the beast, which is, okay, it takes an input signal. It's got a 1K ohm input resistor, a couple of 10 ohm resistors for just to lower the bias down, and so that these guys are a little play well with others sort of phenomena. They don't get into arguments with all the other JFETs because they're all going to be in the same sandbox. But you see, it's a standard complementary JFET follower. You'll be able to put your linear systems parts right in here, folks. And I have chosen, just to make the battery crowd really happy, to run these things at plus minus 13.8 volts. You can power this off of car batteries. Next picture. Oh yeah, this is the one you saw last time, I think. This is the board. It has got 14 rows and 21 ranks. So 14 times 21 times 2 is 588 devices per panel. Okay, next shot. Here's a close-up. And here's the 10 ohm, there's the 1K, here's the P, there's the N's. They're marked. And they just, well, there you go. Okay, next shot. Here's Roth, the gentleman who got to stuff most of this stuff. He's a very patient guy. He's a senior in engineering at Davis. He's going to graduate shortly, and he programs FPGAs for his future living. And he also built me a really spiffy wooden case. You can kind of get a sense of this because it's open partly. And let's go to the next shot. And here they are in their handsome glory. Now, there's two of these panels in each of these boxes. So there's a panel there and there's a panel on the other side, okay? And these are just big, balanced, complementary followers. There are my 45 amp, there's one. 40? Oh, that says 40. 40 amp trip-light 13.8 volt supply. It's got two of them. And use it to power up both of these. I actually have these on display in the past pub, and we are running them on and off, and along with a lot of other amplifiers. they have no voltage gain, so they require a front end with lots of voltage gain. And a fine example of that is a BBA3 or Wayne's latest pass product, which is the XP30 preamp. Now the XP30, Wayne did me a favor and he designed in a couple of features, and one of them is that it'll swing hellacious amounts of voltage, and it also has a tremendous amount of voltage gain. So I can use it as a front end, and I don't have to build them. I just build output stages and listen to them now. And life is good. Next picture, please. Frequency response. Oh, here's where I got the calibration for my AP. It's half a dB. No, it's a quarter of a dB down at 200K. Well, that's pretty good. And that's probably the AP once again. So it's, and it's DC on that end. There's no point in even talking about it. And it's, I don't know, it probably really rolls off somewhere short of a megahertz. I don't have the equipment at the moment to really look at that. And when I look at a square wave, it looks perfect, and that's it, folks. Next picture. Distortion. Here we are into 8 ohms. This is 0001, 001, 01, the whole thing. Here it is in watts driving this. This is into 8 ohms, and it's 1/10 of a watt to 20 watts. This is the part that I always like. You know, 0007, 0009, down around a watt where I actually listen to real speakers. This is probably the, you know, when you consider that there isn't any feedback going on with this, this is the cleanest output stage I have ever seen. And it's not a testament to any genius on my part. It's just having the nerve of stringing a few thousand of them together. It's because these JFETs are really great parts. The problem is that they're teeny. If I can see the next one. They're not that teeny. Here we are into 4 ohms, okay? And at a watt, it's 0015, right around there. And it makes it up to 50 watts. My AP stops at 40 watts. So that's why you'll never see anything greater than 40 watts in this particular set of curves. But drives 4 ohms very nicely. And here you are, you know, less than 1/10 of a percent at 40 watts. Next picture. Of course, we had to find out what's it going to do into 2. Well, actually, we're able to make it crap out a little bit. Somewhere around 20 to 30 watts, you notice it starts flattening out. Okay, so you drive it, and it starts going, I don't feel like it anymore, you know, and right around there. But that's 2 ohms, guys. I mean, come on, give me. My louders don't go down that low. Worth noting here, damping factor on this is about 50, which is for a no feedback effort is doing quite good. And the noise on it is non-existent. But again, these are devices that you would use for front ends of moving coil stages. And so that's the performance into 2. What else we got here for photo? Oh, the distortion curve. Here's 40 watts, 4 ohms at 20 kilohertz. This is about as tough as you're ever going to run this. This is the distortion waveform. And what you'll notice, it's pretty pure third harmonic. This thing is third harmonic everywhere. Partly because the Toshiba parts are good complements of each other. You know, they don't generate a lot of second. And they're also extremely consistent. So when you run them balanced, whatever second is left on these things goes away. And you're left only with the third.
Can I jump in for 1 second? I'm gotta be the only person in the room that doesn't have a clue what this graph means.
Pardon me?
I'll just read this graph. I've always
Oh, this is just, okay, I'm sorry, yeah. Well, in yellow, you got the fundamental waveform. All right, and that's just a picture, just so that you'll believe that I ran that. There it is. And you see it in relation to the what's left over after the fundamental has been removed, and it's been magnified so you can see it. Because this number is, I don't know, 0.01%, or, you know, we could go back, but it's a fairly known number. So when you look at the output of an audio precision on your scope, and you're looking at the distortion waveforms, usually you dial in so you can see the fundamental. That's at 20 kilohertz. And then the secondary channel just displays, here's your distortion. This is what it looks like. What you see is a bit of compression here and here. In other words, this waveform is being squeezed down here, and of course in the opposite direction it's being squeezed, because it's a negative waveform, but it's losing poop, it is compressing subtly, and it's seen in the waveform where this one goes up and that one goes down. That forms a third harmonic. And mostly what you're looking at though is, oh, look how clean and sweet it is. No spikes, no jerkiness, no odd stuff. Next, please.
It's a pause.
Oh, yeah. Well, questions? Okay, well then I'll move right along. Now okay, this is the fourth and last and best part. Adventures with SITs. When I was here a year ago, I had one SIT in my hot little hands and I was waving it around, and I have been able to spend now a full year playing with these parts. And I'm here, I'm trying to treat this particular one as kind of a beginner's guide because I talk to a lot of people and they go, what the hell are you talking about? And what we got here is a transistor that was invented quite a long time ago, relatively speaking, in Japan. And it's a form of JFET. In particular, it's a form of power JFET. Now, I've been fooling around with power JFETs ever since I found that I could actually get a hold of some. And I went through some projects like the ZV9 and ZV8, which used the Leveltech power JFETs, which turned out to have been new old stock. And it turns out that I bought most of them. Then somebody here on DIY Audio, and this is one of the nice things, I get as much back out of participating in this as people get from me. In the case of this, somebody said, oh, Mr. Pass, did you see there's a company called Semi-South making power JFETs? And I went, what? Huh? And I got a hold of these guys. Okay, if we can, go ahead. I got a hold of these guys and ended up buying lots of power JFETs and making product with them. These same people have, in conversations that I had with the development guys, they said, you really ought to try these static induction transistors that government had them make some once upon a time and came and scooped up all the chips and didn't leave any to play with. But they said, but we can make more, and there's probably something that you really want to look at. And I'd heard about it, and they have some legend, and I'm going, oh yeah, well, never really had thought about that carefully. There's some special things about them, though, and there's some exciting stuff that they can do. They're not the end-all, be-all, but they are the answers to certain questions. But the rest of this is mostly about curves. So we all understand curves. Curves on the road, curves on women, curves on transistors. And so a lot of what you're going to see here is just curves. This is a series of curves of a characteristic of a pentode tube. The reason I pick a pentode is because the series of curves that it has looks a hell of a lot like the curves that you get with FETs. They have a characteristic where here's the voltage across the device. This is like the power line. This is the amount of current that goes through the device, and these are the relationships between those two that occur at various control, in this case, gate to source voltages for the part. So, for example, in a pentode, if I just simply ground the grid to the cathode and then run some voltage across the part, I'll see the current go up, and then I'll see it do something like that. In other words, it goes up, and then at some point it kind of flattens out, and then it doesn't vary a lot with regards to voltage. But it varies a lot with regards to voltage at these lower voltages. And all this stuff is also, of course, dependent on the amount of current that you're running. This is known as the pentode curve, and I think this was like a 6550 or something like that. I really don't remember. It's just simply an example for coffee table usage. Next part, please, our next slide. Here's a Mosfet. Now, you notice, same sort of thing. The only thing that's really changed between a Mosfet and a pentode is that the scale has changed. With the pentode, we were running 100 millivolts, 200 millivolts. Here we're running, milliamps, like 100 milliamps, 200 milliamps. We went up to about 400 or 500 milliamps. This goes up to amps. Okay, it is greater by a factor of approximately 10. But down here, the voltages are much lower. They're lower by approximately a factor of 10. So we got the same sort of part, but it operates in a whole different ballpark of energy. The same amount of energy, but at less volts, more current. And the energy is volts times current. But what you do is you see the curve and you go, well, that sure looks like a pentode. And indeed, for the most part, that's what they look like. Next picture, please. Triode. One of our favorite triodes, 300B. That does not look like a pentode. When the voltage goes up, no matter what the control voltage is, when the voltage goes up, the triode continues to conduct more and more current. And this gives rise, though, to well, it does a couple things. One is it allows you to run a tube taking signal off the plate with a fairly low resistance, apparent resistance of the plate. So it forms a fairly low source impedance. But even more interestingly, it has a load line that if you choose the operating points, and a typical load line might be, I want to run this part between, say, here and here. I'm going to have it go back and forth between these voltages and these currents, and I'm going to use that for amplification. You can set that up so the distortion on that would be quite low. And the whole trick with triodes is that you can play the game of load line cancellation. Again, I wrote an article called The Sweet Spot, so you can really read yourself to sleep with that any night. Okay, but this is the triode, and it's distinct from the pentode characteristic. And here's the point that I want to make. Next picture. SITs, invented in Japan. Called VFETs originally, largely because they were in fact vertical FETs, and this was before they had vertical Mosfets, and so everybody got confused. Nowadays they're called SITs, static induction transistors. God knows why they're called that either. So the confusion continues, but we at least try to adopt a name that is consistent. These are the Sonys, that's okay. These are the Sonys 2SK82 and 2SJ28. These are complementary parts. You can build push-pull amplifiers out of them of various sorts, or you can use them individually for single-ended stuff. They have a curve that looks like a triode, if I can see the next one. Here we are. Now, this isn't your Mosfet. There's a little bit of Mosfet-y kind of thing going up here when you get into the relatively high current regions. It's not a pure triode, but it's very triode-like. You'll notice that, in fact, there's a great dependency of the current on the voltage across the device, in addition to what's on the control pin that's trying to set something up. This is the 2SK82. These parts, you can still buy these parts. There's a guy in Singapore who will sell you a few. They are kind of expensive and they're kind of low in wattage. And as our own Mike Rothacker has discovered in his building of amplifiers with them, they run a little low on the gain. But they work, and the distortion is really low. I mean, really low. Next one, please. This is the Yamaha. Now Sony and Yamaha got together, and it was partly financed by the Japanese Ministry of Trade. Let's get these out into the marketplace, and so Sony and Yamaha got a little bit of a subsidy from the Japanese government in exchange for agreeing to actually launch and ship product using SITs. Remember, the SITs were invented in Japan. And so you saw the Sony parts. This was the curve to the original Yamaha part. I don't have a picture of the original Yamaha part, but I'll show you something in a minute. But here was the curve that I've been able to glean together. By the way, these are all thumb in the air kinds of curves. As I point out in a paper that I'm going to, all this stuff is stuff I'm going to publish, and you're just getting it soon. You don't want to try to land a probe on Mars with the data on this curve. But it gives you a feel for what's going on. And in fact, you notice that the Sony was a somewhat smaller part. The Yamaha part was actually a rather high-powered part and is a lot more aggressive in terms of the wattages involved. You'll notice where the currents are getting high and the voltages can actually get pretty high too. This is a beefy part. And interestingly, it looks a little bit more like a triode than the Sony. But again, you don't want to get too literal about these curves. The next one, please. Here's a picture of the remake of this. This was apparently done at the behest of Digital Domain, an outfit in Japan, and built a power amplifier that you can theoretically buy, although as far as I can make out, you can only buy it in Japan. This is ostensibly a 300-watt part. It's a big hockey puck. And I happen to have gotten my mitts on some of these. And if I can have the next, here's the curve on it. It is not the same as the original 2SK77. It's the 2SK77B. It's been slightly re-engineered. And what you see about it when you check it out is, once again, it's all about the curves. It handles more current. It has higher gain. And it's actually, if you start drawing load lines on this, it gets a little more linear yet. This is a really swell part. There's only one downside with this part, and that is that it's relatively huge. The capacitance on it is on the order of 10 nanofarads, input capacitance. So you have to have a drive circuit to drive it. You aren't going to be building any single-stage amplifiers with it. Now, next picture, please. Also, there are the 2SK78B and 2SJ78B. These are small power sits designed for front-end uses. Again, these were put together by Digital Domain. They were not actually made by Digital Domain. Digital Domain had somebody make them. I don't know who that somebody is. I wish I did. But I do happen to have some of these, and they are smaller power parts designed for front-end usage. Next picture. And they have curves that look about like this. Okay, we're looking at milliamps again. This is almost like some kind of 12AX7, 12AT7 kind of part. You got a few mils here. You got a fair amount of voltage out there. But these are, again, very triode characteristics, and but scaled at much lower currents. These are low power parts. Next picture, please. This is my part here. I had some of these made. They're rendered in silicon carbide. They're not as big as the Yamaha parts, but they fortunately come in at about 1/10 the capacitance, so that they're a lot easier to drive. And for the applications that I have in mind, they actually will do a little bit better job. If I was trying to build bigger power amps, I'd probably be looking for either lots more of these or the Yamaha parts. Next picture. Curve on that looks about like this. And we are normally operating this thing in the actual usage that I'm getting and in all the testing I have is real happy right about here, and with a load line that goes like this. And let's see, next picture. Okay, 3 ways to use a transistor. A little bit of tutorial. Common source, common drain, common gate. Common source is the one where you come in the gate, you come out the drain, you've got voltage and current gain. Real common way. If you're building a power amp with only a single gain stage, this is a fairly popular way to do it. Common drain is your source follower. That's the other way of using it. Very common. In fact, people will literally use just this circuit to build FET buffers of various sorts. It has no voltage gain, but it gives current gain. And then the last one is common gate, which gives you voltage gain, but no current gain. Most of the time, it's a cascode connection, but I actually have been building some real nice I to V converters for DACs, where the signal comes in here at a very low impedance and goes back out, and this guy has very low distortion in that mode, and in addition to that, doesn't care anything about the high-frequency digital noise. And so it works rather well. When you look at the triode characteristics of an SIT, there is one, you can use an SIT for any of these, but this is the one that really jumps out at you. It is the case where you're developing voltage and current gain in a part, and particularly if you want to do it with a minimal number of parts, if you want to do it without feedback, if you want to do it without degeneration, or if you want to use those things, fine. But this is the part that if you really want to be a fiend about totally minimalist amplification while still getting some pretty good results, and none of that nasty feedback that everybody's afraid of, or even degeneration, which sounds awful, doesn't it? This is the one. And if I can have the next picture. Oh, I think we're... yeah. Here's a circuit that I have built several variations on. And what is it? Well, it's an SIT. You go in the gate. You got to bias it up. It has a depletion mode. It takes like with the tube, takes a negative voltage on the control pin to set the bias point. So you got a bias voltage out here. This is your input impedance of whatever it is you want to set it at. That's a current source. That could be anything. It could be a constant current source, an unconstant current source. It can be a big fat resistor. A lot of possibilities. Big cap, because there is some DC on this system, so you're going to want to probably do that, or your speaker will talk to you. And the actual speaker. This is a very, very simple amplifier. I have one version of this where the SIT is the only semiconductor in the circuit. And that's not, of course, that doesn't count diode rectifier bridges in the power supply, which I put in the next room. Forget about it. So here we are with an extremely simple circuit. This is where these parts shine. You can use them for followers, and I've done some testing. They work great. But at these prices, you can get other stuff that works pretty good too, and you don't necessarily go leaping at that. And in terms of common gate usages, that's rare enough that, you know, a lot of people just simply go get themselves a nice cheap bipolar transistor and they don't worry about it. I know I do. So this is the application. The raison d'etre of the SIT is essentially the equivalent of the SET amplifier, where you've got a single-ended triode. We have gotten rid of the transformer and replaced it with a cap. I will argue that a good cap is better than a really good transformer from a lot of standpoints. But everybody works with what it is that they can get. In fact, you could drive a transformer with that. Some of these sits come in at 1,500 volts or so there's nothing really keeping you from doing it that way. But the big advantage really is twofold. One, no transformer. The other is really rather good specs. If I can have the next one. Let's see, what do we got? This is my SIT, and this is the distortion. This is it's biased at 2 amps and 20 volts. So it's driving 8 ohms. It's got about 18 dB worth of gain. It's got a damping factor of about 2 or 3, and this is the distortion curve. It's 003 down at low power, and by the time it hits a watt, it's a little over 0.1, and by the time it hits 10 watts, it's about 0.2. And if I want to beat on it a little bit, of course, I can get a little more power out of it. But there's virtually no other device, there's no other transistor I can come up with which by itself will do this job. It's doing voltage and current gain. It's delivering pretty good specs. Now, I'm not going to argue that these are great specs, but I'm going to say that try doing this with any other part. And you can maybe get something, you can get a tube or a multiplicity of other parts to do this sort of trick, but this is the one. And my whole thing is I'm an extremely minimalist guy. I like to listen to the sound of a single transistor, if at all possible. I find that very interesting. And the fact is that done properly, sometimes, even if the specs aren't down in the 000 region on this stuff, it sounds absolutely gorgeous. The fact is, the SIT sounds absolutely gorgeous. You have no idea. Next picture, please. I don't know, is that the same one? I guess. That's slightly different. I just must have thrown another curve in. Okay, if we can just keep on going. Oh, this is a 2SK77B. This is actually rather simple, rather similar set of figures here. This is that big hockey puck operated under the same conditions. The actual case when you compare them is the SIT gets a little bit lower numbers down at low. This is 0.1, you notice, and the other one was down in the 0.01, right? And yeah, actually, this is that. Well, this can't be right. Oh, I know what's wrong. I hand job these scales. That's 1%. That's Can we go back one? I think I screwed up my graph. Because actually, when you go and compare these, or better yet, I think I have one where they're both overlaid. If you go skip up one.
Next one?
Yeah. Oh, yeah, here we are. This is much better. That one's screwed up. This picture, which is unadorned, as you can see, what I do is I try to clean this up so you can actually read these numbers. This is the 2SK77B, the Yamaha parts that the since then Yamaha parts. This is the SIT-1. Can I see that region over there a little bit better? Okay. You notice that this one's actually doing a little better, but it's hitting its sweet spot in the same way that when we looked at the linear systems versus the Toshiba. You can fool around with the conditions on the 2SK77 to get these guys to match up pretty well. So you can't go by that. What you do see, though, in the end is up around 10 watts or so, they converge, they become rather similar. The fact is, though, the bigger chip of the Yamaha part, or what is the successor to the Yamaha part, is capable of being biased at even higher levels. And if you're trying to build an amplifier more than 10 watts, you start either getting ready to parallel a bunch of the SIT-1 parts that I have, or you go and you get one of those 2SK77s, because they can dissipate 300 watts and they can take a lot more current. They are, however, really pretty similar, and that's belied by this curve, which unfortunately just treats my part better because I've got a sweet spot that's closer to that. Next one, please. Bandwidth considerations. This is the part where you see the 10 nanofarad. These are the relative bandwidths between these two parts. You've got high input capacitance on the Yamaha because it's a big, fat, honking chip. And the SIT-1 is a smaller chip. It doesn't dissipate as much power, but it's only down about a decibel or so at 100K. And in the case of the Yamaha at 20K, we're losing 2 dB. So you have to drive it with a low source impedance, which kind of renders it difficult to make a single transistor amplifier out of. On the other hand, nobody's ever bothered to do that, as far as I can tell, with those parts. This will be one reason why. But I want to emphasize, nobody in the 70s, when they were, Yamaha and Sony, when they were playing with these, spent any time thinking about those particular issues. If you look at the circuits that they did, they built 70s kinds of circuits, fairly complicated stuff. Well, I'm sure they had their own good reasons, but I like to make these parts my own if I can. What I find that they're really good for, what they're amazing for, is building little Zen amps. Single stage, come in the gate, come out the drain, bias it up with some passive part, or active if you like, and listen to it. And again, it sounds spectacular. These are parts that are going to be out there before all that long, and these are the kind of things that you're going to be building light bulb amps with or whatever else. And you'd probably be very happy for the most part. Can I have the last picture, I think? Oh, there is one other thing, though. There's something known as a Schad circuit, which simulates a triode with a regular part. The other thing that's worth noting is, at a very low voltage figure for FETs, they operate in that what they call the linear region, which is that triode region we've been talking about in these parts. So if you cascode them at very low voltages, they behave a lot like the triodes that we want. And there's two ways of doing that. You can cascode them at only a few volts, and for reference, I send you to the Zen Variations number 8 and 9, where it's exactly what we did. We ran little power JFETs at fairly low voltage. They were in the linear or ohmic region. These effects for distortion cancellation were all in play, and they work. Or you can do this other thing, which is known as, it was invented by a guy named Schad, who actually did it for tube circuits. And as I recall correctly, he was turning pentodes into triodes. There's a little feedback loop on this of relatively marginal amount. And what it does is it takes the characteristic of, and this is one of our favorite MOSFETs, the IRFP240, and you look at it, and here's that old MOSFET curve. By the way, I lifted this off of DIY audio. Somebody here may have generated this and is not being given credit. But here's your classic MOSFET. Over here, however, same FET in this circuit, again known often as a Schad circuit, you see the triode characteristic. You can go in and you can play this game with those kinds of parts. The notion of using this region, though, and again, it's known as the linear region on FETs, and some of them have broad ones and some of them do not, you can get some of these effects. The problem is the capacitances and the voltages and everything are very problematic, has to be done very delicately. Essentially, nobody's doing it. It's safe to note, though, that SITs, are, for all intents and purposes, are these parts, but the linear region, this here, has been extended out over the entire operating curve. That's really the real difference. Other than that, they're just like power JFETs. I'm not sure. I think there's one more. Mike Rothacker, who published the Circlotron amp project on DIY audio. He's a real smarty pants, let me tell you, because I'm working on this and I find out he's doing the same thing. He got a hold of some of the Sony 2SK82s and he built himself one with the light bulb amp, the D-Light, but with the SITs. And then we started corresponding and he decided he would even go one better. This is a roll, in fact I recognize the former, is by MWS Industries, of a giant roll of copper wire being used as a coil, as a load for the Sony part. And he gave me this picture so that I can tell you about this. This is another article coming up. This is Mike Rothacker's single-ended sit amp off of the Sonys that you can still buy at about 20, 25 bucks a shot. Well worth it. The distortion figures on it are really low, I know for a fact. The only thing you can say is that the gain is not real high. You might have to turn your preamp up a little bit. Next picture. And that's the end of our program. Question?
You said something about that they were originally designed by the Japanese government and then Sony and Yamaha took them. What was that?
They were designed by a Japanese professor, and now I've forgotten his name. It does just say, pardon?
Ishikawa.
Thank you. Professor Ishikawa. In fact, there's some questions as to exactly when he may have done. They may have done it much earlier, but somewhere in the late 60s, it surfaced and became of interest. Interestingly, it's a real thing, and it's a real phenomenon that really works. And in the West, it took a while for anybody to take it seriously. And then when they did take it seriously, it was, well, on the one hand, you had Sony and Yamaha making VFET amplifiers, but somewhere prior to that, the Soviets and the US military both realized that they made wonderful radar parts. And so they began, particularly the Russians, because you can actually find quite a variety of Russian SITs. I haven't had access to any of them, but I've seen a lot of data sheets. And they're radar parts. They're very, very fast. They switch incredibly fast, and they take high voltages. So, also, well, in the case of the ones I'm playing with, one of the applications, if you want to put a probe on Venus, these chips don't melt until 800 degrees centigrade. They literally have the potential for having a little quartz window over it, and you can run them at temperatures where they glow, and thus completing the cycle of imitating a tube.
My second question is, how fragile are they, or do they have any special handling precautions?
I haven't lost any yet. I haven't lost any. You know, I've had. Now, it's not like there's no issues to these parts at all. Okay. One of them is that they are not Mosfets. That is to say, they have some gate leakage. Okay, so when you fire them up and you're biasing them in depletion mode biasing, there's a certain amount of current that comes out. The figures on these power parts range anywhere from less than a microamp to as much as 100 microamps. And up around 100 microamps, you start looking at them with a little cold fish eye. But they still work fine. You just have to allow for that, that factor when you do it. Now, I have been told by a gentleman at Linear Power, I'll keep him unnamed so he doesn't get embroiled in any controversy, that one of the issues with the Sony parts originally was that they suffered hot carrier injection, which would be a super version of leakage. And his thinking was is that some of the complications of the circuits surrounding those parts were there to deal with those kinds of issues. To date, I have been very lucky, probably due to more modern processing that the manufacturers can achieve. I haven't had any real issues, but I do have to. And if it's a case where it really counts in terms of having low leakage, you have to select them. Some of them have almost none. Some of them will leak 100 microamps. So if it's important, you sort for it. And if it's not important, you just make sure that they work. It's okay.
Thank you.
Yes?
So when you're drawing your load line for an output stage, you're actually looking at like an 8 ohm or a speaker?
Yeah, typically.
Oh, okay.
I mean, not necessarily. One of the things that's kind of cool that I'm doing on a product, and again, Smarty Pants Rothicker is doing exactly the same thing, is the SIT amps that I have a stereo amp that you can go here in the pass-room. It's sitting right next to the Beast with 1,000 JFETs. It is fixed. I set the load line at a fixed figure, and it is slightly lower. It's set for lowest distortion. It's slightly lower than 8 ohms. And in point of fact, that's where it sounds the best, even if it's 8 ohms. Ideally, if you get something like that and you don't have any feedback or anything else, you have an opportunity to play with the load line a little bit. And it's not hard to adjust the load line on these. And so I have a model which is a monoblock, a little snazzier, and it's got a meter in front that reads load line figure and a knob so that you can tweak it against the specific loudspeaker. Because there is an optimal spot for any given load and or any given listener. So this is one of those things where there's a nice green zone and you can be anywhere inside the green zone that you like that makes you happy, but you are adjusting the load line. Any others? Yes?
What's the output impedance?
About 3 ohms typical. And the gain on the ones I'm making, the gain's about 18 dB. And the input impedance is 47K. And the noise is low and clips at 10 watts. All done.
Okay.
I'm done. Thank you very much.